Hi, Assalamualaikum. We are from Group 1 and we will be presenting on the topic diode. Our group consists of 7 members which are listed as beside here.
Structure of diode. The first diagram shown a picture of diode and the second diagram shown how it looks like inside a diode. Diode is made of semiconductor materials such as silicon and germanium. Diode, in its fundamental form, is a PN junction device through which current flows when the proper forward potential is applied. In PN junction, it has P-type, N-type, and depletion region. P-type is at the anode terminal and N-type is at the cathode terminal. And in the middle, it has depletion region. The P-type has holes as its majority carrier and electrons as its minority carrier, as against the N-type material has electron as its majority carrier and holes as its minority carrier. For depletion region, it is a layer of immobile or unmoving ions. Function. Diode is a two-terminal electric component that conducts electric current in only one direction. It is a two-terminal device normally formed by fusing P and N-type semiconductor material, each having majority and minority carriers. It has two conditions, which is forward bias and reverse bias. Forward bias is when P-type connected at the positive terminal and the N-type connected at the negative terminal. It is vice versa for reverse bias, which N side is connected at the positive terminal, while P side connected at the negative terminal.
The standard diode symbol is represented as above. In the above diagram, we can see that there are two terminals that are known as anode and cathode. The arrowhead is the anode that represents the direction of the conventional current flow in the forward bias condition. The other end is the cathode. Next, where are the diodes commonly used in electronic circuit? The answer is in the rectification circuits. A rectifier is an electrical device that is made of one or more than one diodes that converts the alternating current AC into direct current DC voltage. It is used for rectification, where in the diagram besides shows the example of a full-wave bridge rectifier uses 4 diodes to convert both half cycle of the input AC into DC output. Here, I will explain more on how the full-wave bridge rectifier works. Firstly, during the input positive half cycle, the diode D1 and D2 becomes forward bias, while D3 and D4 becomes reverse bias. The diode D1 and D2 form a closed loop that provides a positive output voltage across the load resistor RL. On the other hand, during the negative half cycle, the diode D3 and D4 becomes forward biased, while D1 and D2 becomes reverse biased. But the polarity across the load resistor RL remains the same and provides a positive output across the load.
For next part, so where are diodes used in everyday life?
Real-world application for diodes. Firstly, rectification in power supplies. We use diodes for converting alternating current to direct current. By allowing current to flow in only one direction, diodes help eliminate the negative half cycles of the alternating current waveform, resulting in a smoother DC output. For example, AC laptop adapter. When you plug in your laptop charger, the rectifier diode inside it converts the alternating current from the wall socket into direct current, which powers your device. Secondly, light emitting diodes, LEDs. They emit light when current passes through, providing clear visual signals. For example, traffic lights, toys, household lighting, or electronic devices. Lastly, photodiodes. Photodiodes are light-sensitive diodes used in applications such as optical communication, light detection, and photovoltaic system. It converts light energy into electrical energy. For example, solar cells and calculator.
Next, I will explain to you guys the comparison between our assigned component, which is diode, with other power electronic components. The first characteristic is voltage rating. What is voltage rating? It is a range of voltage that a device can operate at safely. We can see from the slide that Zener diode range from 2.4 volts up to 200 volts, depending on the specific type of Zener diodes. They have a specific voltage rating at which they operate in reverse bias mode. Hence, Zener diodes can be found with precise voltage rating. As for Schottky diodes, they do not have specific voltage rating like Zener diode. Instead, their maximum voltage rating is determined by their reverse breakdown voltage, which can range from few volts up to several hundred volts. Next, we have IGBTs, which is known for insulated gate bipolar transistor. We can see from the slide that IGBTs have a high voltage rating ranging from hundreds to thousands of volts. This is because they are commonly used in high power application. Also, these devices are typically used in power control applications such as motor, drive, inverter, and power supplies. Lastly, we have triads, which is known for triad for alternating current. They have a voltage rating ranging from few tens of volts to several hundred volts. Hence, they are commonly used in AC power control application. Second characteristic is current rating. What is current rating? Current rating is the level of current which an appliance or device can carry safely. Firstly, for Zener diodes, they have relatively low current rating, typically ranging from few milliamperes to few amperes. Hence, they are primarily used for voltage regulation and stabilization. Next, for Schottky diodes, they have a higher current ratings compared to Zener diode, typically ranging from few amperes to tens of amperes. Thirdly, we have IGBTs, which is known for insulated gate bipolar transistor. They have significantly higher current ratings compared to diodes, ranging from tens of amperes to hundreds of amperes, or even thousands of amperes. Lastly, we have triads. They have current ratings that are similar to IGBTs, typically ranging from tens of amperes to hundreds of amperes. Third characteristic is switching speed. Zener diode and Schottky diode are both used as voltage regulator in electronic circuits. While they do have fast response times, they are not typically used for high-speed switching application. On the other hand, IGBTs, which is known for insulated gate bipolar transistors, and the triads, which is known for triad for alternating currents, are both used for high switching speed application. To summarize, Zener diodes have low switching speed in range of microseconds, while Schottky diodes have faster switching speeds in the range of nanoseconds. IGBT have a moderate switching speed in the range of tens to hundreds of nanoseconds, and triad also have a moderate switching speed in the range of microseconds to milliseconds.
Next, the comparison between diode with other power electronic components in terms of advantages. First, Zener diode. The first advantages of Zener diode is voltage regulation. Zener diodes are commonly used as voltage regulator in electronic circuits because they can maintain a nearly constant output voltage. Second, simple voltage regulation circuit. It is simpler and more cost-effective compared to other voltage regulation method because it only needs fewer components and easy to design. Third, stable temperature characteristic. Zener diodes are suitable for application where temperature fluctuation might affect the performance of other components. Next, Schottky diode. The first advantages of Schottky diode is low forward voltage drop. This characteristic leads to reduced power losses and increased efficiency in electronic circuit. Second, high operating temperature. Schottky diode can operate at higher temperature without significant degradation of performance. Third, suitable for low voltage application. Schottky diodes are well suited, especially those where a low forward voltage drop is critical for efficient operation. Next, IGBT. The first advantages of IGBT is high voltage handling capacity. IGBT can handle high voltage level, making them suitable for application where high voltage is required. Second, fast switching speeds. Fast switching is necessary to control power flow and minimize switching losses. Third, simple drive requirements. It simplifies the design of control circuit and reduces the complexity of the overall system. Next, triac. The first advantages of triac is bidirectional conduction. Triac can conduct current in both directions, regardless of the polarity of the alternating current. Second, low cost. Triacs are often cost-effective components. Third, ease of integration. Triac can easily integrated into existing AC circuit without requiring major modification. Next, the comparison between diodes and other power electronic components in terms of limitations. Zener diode. The first limitation of Zener diode is power dissipation. Zener diode has a maximum power dissipation limit. Exceeding this limit can lead to overheating and potential failure. Second, current sensitivity. The voltage across a Zener diode is affected by the current flowing through it, which may impact the accuracy of the voltage reference. Third, noise sensitivity. Zener diode can be sensitive to noise, which may impact their performance in certain electronic circuits. Next, Schottky diode. The first limitation of Schottky diode is low reverse breakdown voltage. This makes them less suitable for applications that require high reverse breakdown voltage. Second, limited power handling capacity. Schottky diode may not suitable for high power application due to their limited power handling capacity. Third, higher cost. In some cases, Schottky diode can be more expensive than other PN junction diodes. Next, IGBT. The first limitation of IGBT is switching losses. This can result in power dissipation and reduced efficiency, particularly in high-frequency applications. Second, temperature sensitivity. As temperature increases, the on-state voltage drop may also increase, affecting the device efficiency and power handling capacity. Third, size and weight. IGBT can be relatively large and heavy compared to other semiconductor devices. Next, triac. The first limitation of triac is voltage and current ratings. Triac typically have limitation on the maximum voltage and current they can handle. Exceeding these ratings can lead to device failure. Second, limited to AC applications. Triac are designed for AC application and cannot be used to DC power control. Third, low gate impedance. Triac typically have a low gate impedance that requires careful design of the gate drive circuit.
Diode in a real-world application is charger. Charger often work with alternating current AC from the power source. Diodes are used to rectify AC into direct current DC, allowing the current to flow in only one direction. This is crucial for charging batteries, which typically require DC. So, which means is diode is usually convert AC current into DC. So, as we can see, this is a charger. If we open this pipe, it can see it has a Schottky diode and Zener diode. Next is failures or unexpected challenges diode in charger. For the first point is voltage drop across diode. Diode failure if it exposed to higher current that can handle. So to meet the requirement is low forward voltage drop. For the next point is AC current leak during the charging process. Okay, let's see, we leave our battery to charge, but several hours later, we find out that it has not even eaten half charge. This could mean that AC current leak during the charging process, hence the slow charging rate. So to meet requirement is check the wiring and connection. For the next point is movement of current in reverse. In another cases, the battery may be discharging instead of charging. A diode can be culprit whereby it facilitates the draining process in the circuit. The backward movement of current could be caused by a damaged diode. Therefore, to meet the requirement is using reverse bias protection.
Another case study is bypass diode in solar panels. This is to prevent the application of high reverse voltage across the cells in the event of shading. Basically, it is to remove the hotspot phenomenon that could damage the PV cells and even cause fire if the incident light is not uniform at the cell surface in a module. Hotspot phenomenon is the excess power dissipation. Particularly, bypass diodes are used in solar PV systems to protect the partially shaded cells from fully operating cells in the full sun within the same module, which are connected in series. If a PV cell is in a shaded area and there is no bypass diode but having a blocking, in that case, the shaded cells does not produce any current and the current will flow through the shaded cells due to the voltage potential. The shaded cells will work as a load or semiconductor. Thus, it seems to be a hotspot which could completely damage the cells. The photo shows the bypass diode in the junction box. However, there are also failures of these bypass diodes. Some of them are electrostatic discharge, lightning strike, and thermal runaway. For thermal runaway, partial shading of a solar PV cells causes the diode in the shaded area to go into forward bias, increasing the temperature and power dissipation. If the shading persists, the diode stabilizes at thermal equilibrium. But if the shading abruptly disappears, the diode will shift into reverse bias. If the reverse power dissipation exceeds the junction box's heat dissipation capacity, the diode undergoes exponential temperature rise, increasing the reverse current and power dissipation. This destructive cycle continues until the diode is overheated and ultimately destroyed. The photo shows the failure of diode because of the thermal runaway. There are also other failures internally where there are impurities and crystallines of the diodes, and shunting will cause a short circuit of the cells.
This is the references for our presentation. That's all from us. Thank you.